Good evening, everyone. I welcome you to this talk series, CS Katha Barta, where we invite academics and professionals to deliver their talks. Our guest for today's talk is Professor Srini Devadas. Professor Devadas is the Webster Professor at of EECS at the MIT, where he has been on faculty since 1988. His current research interests are in computer architecture, computer security, and applied cryptography. In 2021, he received the IEEE Cybersecurity Award for Practice and the ACM SIGSAG Award for Outstanding Innovation for his work on secure hardware. Professor Devdas is McVicker Faculty Fellow and an Everett Moore Baker Teaching Award recipient, both considered MIT's two highest undergraduate teaching honors. Today, he will speak about PAC privacy. I welcome you, Professor Devdas. And without further ado, I invite you to take the virtual stage and begin your presentation.
Great. Thank you so much for the kind introduction. Yeah, so this talk is on computer security, in particular data privacy. I want to point out the first name on the author list on the slide, Hanshin Shao, who is a senior PhD student who really did the lion's share of the work. So really, we're trying to address a very generic problem. So you have some sensitive data. It could be messages, email messages, files, images, what have you. And we're going to process it. This processing function is written as M. And so we end up producing an output, M of X. And it could be some real value d-dimensional output. And we want to now expose M of X. So we're not exposing X, but we're exposing M of X. Now, M, it could be simply the mean or the median of the data set. And as I said, X could be multidimensional. D could be in the millions, for example, or D could be 1. So one example where D would be in the millions is if you had machine learning model, a neural network that you expose. So what that means is M of X is the training process on data X, and it produces a neural network with a bunch of different parameters. And now you want to publish this neural network, and maybe it's taken lung scans as an input, the neural network, and tells the person whether the person has cancer or not. And this would be good to expose so people can use it if they want. But now you're concerned about what the leakage of individual patient data is that's in X when M of X is exposed. So and then the third example would be that you have side channel information. So people are really concerned about side channel leakage in processors and software. There's been examples where you look at cache and miss patterns and discover secret keys. And so M of X could be the cache hit or cache miss patterns associated with if you're running a program that is doing encryption or decryption using some secret key, which is a sensitive data. So it's a fairly complicated situation there. So obviously, an important problem. People have worked on it for a while. There's been some approaches, and I'll say a little bit more about that. But hopefully that sets the stage here. So when we start with a problem as generic as this, we have to start asking fairly deep questions, broad questions like, what is privacy here? What are you concerned about with respect to X itself? So is it just, let's say, is your salary? Is it a number? Is there something more complicated associated with it, where you have linkage between individuals and their DNA, for example, what have you? And you also say, what is it that the adversary should be prevented from doing? So the adversary should not guess or recover your secret data, and it might be that just getting 80% of the information corresponding to a secret key is going to break the entire system, because you can brute force the remaining 20% of the bits. So you got 128-bit secret key and 100 bits are exposed, it's done. If you have some input-output relationship with respect to encryption and the decrypted text, ciphertext and plain text, you can get the remaining bits just with a simple brute force attack. And you ask, what kind of adversary and what kind of power. So what will you do? How do you prevent a computationally unbounded adversary? How do you prevent an adversary who's poly time bounded? Different assumptions. The thing that's actually more complicated, or actually more involved than just this computation restriction, is what is the prior knowledge of the adversary? This corresponds to context. So does the adversary know that X corresponds to lung scan data, or X corresponds to salaries? Does the adversary know that M of X is a neural network with the parameters and it's resonant 50? Does the adversary know that the ranges of salaries of, let's say, MIT professors, are from 0 to whatever, hundreds of thousands of dollars or what have you? Same thing, maybe it's just arbitrary populations. So you have to specify the prior knowledge of the adversary. You can think of this as including the context that the adversary is trying to run their inference task. Now you also have the mathematical quantification of inference hardness. So again, do you want 80% of the secret key bits and that's enough, or do you need 100%? How can we say something about images? Finding features is fine, or you need to get the pixels exactly right. Now, how do we measure this hardness? So those are the two questions you need to answer. And depending on how you answer these questions, there's different definitions of privacy. Right? So there's a few definitions that I want to go over just because we want to get the terminology right. And this has been really decades of work in various definitions, and we're going to propose a new one. So the classic definition is Shannon perfect secrecy, which is a very strong definition in this context, statistical indistinguishability, and that says for any possible inputs X and X prime, the distributions M of X and M of X prime are identical. And so you get exactly the same Gaussian distribution for X and X prime if you feed them into M of X and M of X prime. And so this is obviously very strong, and you kind of go and you say, wait a minute, if M of X is this rich training process for a neural network, how can I possibly imagine that for dramatically different X and X prime that I'm going to get the distributions of M of X and M of X prime to be identical? And the bottom line is that in that case, you really can't expose the M of X. So it's a very strong, the strongest criterion you can imagine, but it's unusable, really. For things like one-time pads, and when you do communication using one-time pads, you can use this definition, but then of course, then you say, how did you share the one-time pads? It's really a good stake in the ground, but really hard to use, Shannon perfect secrecy. Then you have something that's used a lot under various computational assumptions. The cryptographers love this. You're talking about a computationally bounded adversary here, and you say, you know what, the distributions of M of X and M of X prime are indistinguishable for a computationally bounded adversary. And you have to make some assumptions with respect to what the adversary can do and can't do. You also have to say something about indistinguishability. You could say that indistinguishability corresponds to essentially a polytime bounded adversary, and say things corresponding to the distance between the distributions, yada, yada, yada. But mostly, the schemes that are used for data privacy fall into the last category here, of which differential privacy is probably the most popular definition. And DP says for any two adjacent data sets, X and X prime, the divergence of the distributions. So we're not talking about the distance between the distributions, and you're specifically using some divergence function. So D alpha is called alpha divergence. So sometimes we say DFF, and I'll say that which is F divergence. And there's many different functions F or functions alpha that you can use. But what you see here is you're looking at the probability distribution of m of x and the probability distribution of m of x prime. And this bar in the middle here signifies the divergence between the two. So just think of it as distance. And you're saying the distance is bounded in some fashion. And so that essentially says you're going to make it hard for the adversary if this distance is bounded for them to distinguish between m of x and m of x prime. Notice that what we did here was talk about a problem where you're giving the adversary two things and asking them to guess which one is x, came from x, and which one came from x prime. So it's all about distinguishability. It's not about reconstruction. Reconstruction would be, I've discovered that one of the secret images that was in the data set X, kind of looks like this professor from the National Institute of Science or what have you. And you can essentially define your divergence function for the distributions, but you also say that the adversarial problem is not one of distinguishability, but it's one of reconstruction. And that's what we're going to do. But in differential privacy, we're really talking about, I'm going to give you two things, and differential privacy says the adversary can distinguish between these two things. You'd like to say that. And the way it tries to get that is by talking about the bounding of the distributions, right? Okay, so let's get going. We want to now do something a little bit different. And the reason we want to do something a little bit different is because these definitions have some limitations. So we want to do the same bridge between semantic privacy and mathematical quantification, like I just described. And we're going to say things like, well, I'm going to tell you that the adversary knows all the public parameters. The adversary knows that your secret images are about pets or portraits of people. And then we're going to set an adversarial inference task, and we're going to set a lower bound on the failure rate. So we're going to say that the adversary is going to fail with a minimum failure rate of 99%. So the success rate is at most 1%. And maybe the task is the adversary cannot guess even one bit of your secret key with probability more than yada, yada, yada. Or there's an L2 norm criterion for reconstruction, and the error in the L2 norm is going to be something that's that is greater than this failure rate. It could be 1/2, it could be 3/4, or what have you. And once we do that and we specify that, we want a privacy preserving scheme on this particular objective processing function M, right? So this seems pretty abstract because I've really talked about everything symbolically, but we're going to eventually end with concrete examples. But now we have to really get into trying to specify each of the things that you see in the slide more precisely, right, mathematically. So here's the overall flow, right? So we're going to essentially say that there's some prior knowledge that corresponds to the adversary. And really, to cut to the chase, I'm going to say that X is drawn from some distribution. And we'll talk about how you can think about, the cat images in CFR 10 or what have you being drawn from some distribution. We'll get to that, but let's assume that. That's the prior knowledge of the adversary. We're trying to quantify that. We're going to talk about a particular target inference problem, and that could be just exact reconstruction, or it could be 90% of the pixels should be exactly the same. The other 10% you don't care about. So knowing this, and you haven't exposed anything yet, you can essentially use probabilistic analysis and say, if I started randomly guessing, or an adversary started randomly guessing, what is the prior success rate of the adversary? So if you had 10 numbers and they were uniformly distributed as whole numbers from 0 to 9, then the adversary has a 10% guess rate of getting the number correctly, 1 out of 10. Right? So that's all you do. Then you expose M of X, and you want to compute the additional leakage. Obviously, that's a little bit harder than what I just described. But if you get that additional leakage in terms of a probability, then you can add that probability to the prior success rate and get your posterior success rate. Right? So you can do the prior success rate, and then you got this independent exposure, and so you can add these probabilities together. So our goal is going to be to figure out what this additional leakage is, because obviously that's a function of M of x. But once we have that, and this is usually called the posterior advantage. So the prior success rate and the posterior advantage is the posterior success rate. Right? So we need a little bit of mathematical preparation. We're going to guess x tilde as the adversary's guess on the sensitive data x. We're going to have a success criterion, and the success criterion could be arbitrary. It's something that says rho, when it's given x tilde and x, is a 1. But this could be an 80% parameter embedded inside of rho, which says that x tilde and x are within 20% of each other. So there's 80% of x tilde is the same as x, right? Or it could be 90%. Rho could be arbitrary. We have the optimal prior success rate that I just described to you for the simple whole number example, and it's going to be delta 0 rho because it depends on rho. And the success rate is usually 1 minus delta, and because the prior failure rate is delta 0 rho. And I described to you of what an example computation of delta 0 rho would look like for this whole number example. And then the posterior success rate, that the adversary can return satisfied x tilde such that rho x tilde x is 1 after observing the release, right? And then the posterior advantage would be delta 0 minus delta. So this delta 0 rho is going to be greater than delta because things obviously get better for the adversary in terms of the failure rate. It shrinks when the adversary sees M of x. Right, so you've got a positive quantity here because delta 0 is greater than delta. Okay, so not too complicated so far. So now let's talk about PAC privacy. So where does this name come from first? PAC stands for probably approximately correct, and PAC learning is about a theory of the learnable proposed by Leslie Valiant, and we use that terminology, the terminology of PAC learning. And so PAC learning was really about whether it's easy to learn or not. We just use the terminology, but we are talking about wanting to say that something is hard to learn. We want to talk about the failure rate of learning and make the failure rate large. So we reverse it. Easy is bad for us in terms of security. We want to make things hard. And so the basic definition I've actually kind of already given you, but it's all up here. I'm not going to read it out, but essentially says the user generates data X from some distribution. We'll talk more about that. Sends M of X to an adversary. The adversary knows the distribution that X came from, but doesn't know what X is. So like I said, it could be that I'm selecting 5 numbers uniformly, randomly from 0 through 9 with replacement or without replacement. That would be your D. And M could be the average of these 5 numbers is exposed to the adversary. And then the adversary is asked to return an estimation X tilde on X with this rho criterion, and the success rate should be at least 1 minus delta, or the failure rate should be less than or equal to delta, right? So far so good, I hope. Excellent. So now math gets a little more hairy. We have to talk about how we're going to actually bound the posterior advantage, and we need a little bit more. So we're going to use mutual information. Mutual information is a well-studied quantity that is defined a couple of different ways. The definition that you see here uses KL divergence, that stands for Kullback-Leibler divergence. So this is an example of F divergence, and I'll tell you what KL looks like in a second. But it essentially says that you have the joint distribution of X and W for any 2 random variables in some joint distribution when you're W could be M of X and X could be, well, X. And so you're looking at the divergence between the joint distributions and the product of the marginal distributions of X and W. Right? So you don't need to understand this deeply. Think of it as a definition, and it's obviously if you have these distributions, you can compute the KL divergence, and you can generate these distributions using trials. And so you can think of X being, and this is what we're going to do, X being randomly sampled, and then you send out M of X. That would be one trial. Keep doing this. You look at these distributions, and you can compute the mutual information. And so another way that may be actually more popular that you might have heard of computing the mutual information, or I should say defining the mutual information, is being expressing it using entropy. So mi of xw is the entropy of x minus the entropy of x when given w, so the conditional entropy. So you're saying the mutual information is essentially the correlation and that the difference between what entropy is left when you know w. That would be h of x given w, and when you subtract that out, that tells you what the mutual information is. Alternately, h of x conditioned on exposing w would be entropy of x minus the mutual information, right? So you're giving away something because the adversary sees m of x, and when the amount that you give away is the mutual information, so what's left is h of x given w. So it works both ways, right? So these two definitions are equivalent, right? They're mathematically equivalent. Obviously, that I haven't told you what the exact definition of entropy is, but that's not going to be important because we're going to go with the former definition, the Kullback-Leibler definition. But I just put this up because you might have seen this and not seen the KL divergence definition. They're the same. So we have to do a few things, obviously, and the first thing we're going to do is try to mathematically bound the posterior advantage. Okay, and so here's the theorem. But I want you to focus on the last line of the slide, which is about as simple as it gets in terms of a theorem statement. Right. So what is the last line saying? Well, on the right-hand side, you have the mutual information between x and m of x, which is obviously defined based on KL divergence, given what I just told you. On the left-hand side, you have the KL divergence corresponding to delta, which is the failure rate. And what you really have here, and actually in this case, you might want to look at the line that corresponds to df higher up. And so delta KL, you can think of as df of the so df between the Bernoulli distribution of delta and the Bernoulli distribution of delta zero, right? So again, I mean, you think of this as you're running a whole bunch of trials, and at some level you can intuitively think of this as that difference between two probabilities. So total divergence, by the way, would just be delta zero minus delta. When you talk about F divergence, you're talking about the Bernoulli variables, one delta and one delta zero, and you're talking about the divergence between the two. So what we're saying now is we have a bridge between mutual information and failure probability. That's all you want to take from the slide, or that's all you should take from the slide, which is this theorem that says there's a connection, and it's not a complicated theorem. I won't prove it, but it's in our paper. You can read it offline. That connects the failure rate on the left-hand side and bounds the difference in failure rates by the mutual information. So if in fact you viewed the left-hand side as delta zero minus delta, then that's obviously easier to think about. But in reality, if you want to use mutual information, you have to think about it as KL divergence. So I didn't really even define KL divergence, but essentially it's D of F. The F would be x log x, and you can look that up. It's not going to be important. The intuition is really what you want to take away from this slide. There's a bridge between failure probability on the left-hand side being the difference in failure probabilities being bounded by the mutual information. And this kind of makes sense. I mean, it obviously, hopefully is intuitive, because I mean, if you have more mutual information, Well, I mean, you're going to get a bigger bound. It's less than or equal to, zero point 0.4 versus less than or equal to 0.2. 0.4 it corresponds to a larger mutual information. And so now the adversaries failure probability, could drop by 0.4. So they had a failure probability of 0.8. It drops by 0.4 to, well, again, 0.4 because mutual information is 0.4 or what have you. There's another interesting thing here that I want to point out, which is that mutual information itself doesn't depend on rho. It doesn't depend on the specific reconstruction problem. That makes sense in the sense that why would the conditional entropy of the mutual information be dependent on the specific reconstruction problem that the adversary has? And now obviously rho is there on the left-hand side, and there's a nonlinear relationship between a delta 0 rho and delta if you use KL divergence, because as I said, the f function KL divergence is x log x, and you would actually have to numerically compute the delta. If I gave you a delta KL small delta, and then I said this is less than or equal to 0.4, and then I gave you small delta 0 rho, in order to compute delta, you'd have to solve this numerically. But in the case of total variation, like I said, you would just subtract and you would get that example that we had there. So what you want to take away from the slide is simply that mutual information can bound the posterior advantage. That's it. If you can shrink down mutual information, you are shrinking the posterior advantage in exactly the way that you see here on this slide. We could do a simple example, right? You're probably thirsting for an example. Here's a simple one. When data is of sufficient entropy and the processing has a closed form, you could create a noisy, obviously m of x by perturbing it and so on and so forth. But if you in fact have a bunch of entropy in the data, then you don't have to add noise even to get a packed privacy bound. Okay. So let's take a look at this example where you have the mean estimation of Gaussian data. Suppose we have x being taken from some distribution, which is in this case it's just n01, and we have these IID samples corresponding to, well, these numbers. And we could obviously do this from any distribution, but let's just say that this is IID. Well, you could use a mutual information either definition, and you get the mutual information as shown on the slide, right? So the mutual information when you have some IID variables corresponding to n-1 variables, and you have a single variable to sensitive data now, and you're taking it from n01, then the mutual information is as shown here, which is simply a summation that you see on this slide. Now you could use the entropy definition and compute the mutual information down below, and so you have 0.5 log 1 plus 1 divided by n-1. Sorry, when I was pointing to this, m of x is simply the average here, the mean estimation. So I think I called m of x mutual information. Sorry for the confusion, but m of x is basically what you're publishing, which is the average, really simple mean estimation example. And m of I is the mutual information, and that's down at the bottom. So if you look at what we have, the last equation on the slide, bottom right, you're seeing that you have, for finite n, you have a finite quantity. And as n goes to infinity, this quantity goes to 0 because you end up getting log of 1. So what this says is the mutual information as n goes up to large numbers, when you just publish the average of a bunch of large numbers, well, that mutual information goes to 0, which is very intuitive. So basically, it tells you that if you use the previous theorem, for any given finite n, and as n grows, mutual information shrinks, and your posterior advantage is going to shrink as well. And so you can use this bound to show privacy. You can bound the failure rate of an adversary for an arbitrary inference problem, or bound the posterior advantage, I should say, by using this closed form mutual information equation. And so this is our first security problem that we've essentially, well, solved in one way, where we've said, here's this M of X, it happens to be a mean estimation problem. I gave you the distribution, I gave the adversary the distribution, I've computed the mutual information in a closed form, I've shown you that it's finite, and therefore I've bounded the posterior advantage. And what is my prior success rate? Well, my prior success rate can be computed because I gave you the distribution, and it's some number, but I can also bound the posterior failure rate because I bounded the posterior advantage. And along the way, I did not have to add any perturbation up to M of X, but there are definitions like differential privacy that I'll now contrast with, where you would have to do that, right? So I don't know how much you know about differential privacy. I'm not going to assume very much. And I'm going to explain what DP in this example would do. So again, same thing, M of X is mean of X. The records are a scalar in 0 and 1, and you compute what's called the global sensitivity of M, which in this case is the mean, and in this case is 1 over N. Okay, so the sensitivity is basically defined as what happens when you change the inputs, to the outputs, and it's basically a fairly simple intuitive characterization of output dependence on the input. So in this case, for means, the sensitivity is 1 over N. And what differential privacy says is that we could use the Laplace mechanism and output M of X plus Z, where Z is given by this equation, but the key is that it's 1 divided by N times epsilon, right? So at the denominator, you have N times epsilon. And epsilon equals 0 is perfect privacy. That's equivalent to Shannon perfect secrecy. And epsilon is finite number is some level of privacy, and no privacy when epsilon equals infinity. So in differential privacy, even if N were large, but let's say it's some fixed large number, you would, if you added no noise and if Z were 0, then effectively that implies that epsilon equals infinity, which means you have no privacy. So you have to jiggle the output in the definition of differential privacy. You have to jiggle this mean that you've exposed by a little bit, and it's a small quantity if N is large, it's a larger quantity if N is small, in order to get any finite bound for epsilon, which says that you have some level of privacy. You have no privacy for epsilon equals infinity. And the only reason for this example is to give you also I wanted to introduce perturbation because we're going to go back and have to use it for more complicated examples, even in the case of packed privacy, but it sort of tells you how you can prove privacy in 2 different ways, in the packed privacy way for this simple example, and in the differential privacy realm for, again, the same example. Right. So it's hopefully a nice contrast. So we're going to go back to packed privacy, and I want to talk a little bit about exactly how we would analyze the privacy. We can compute mutual information in an automatic way because it's essentially an entropic quantity, and we can use Monte Carlo trials to compute the mutual information. So let me tell you exactly what's going on here. So I talked about the simple example where you can compute mutual information in closed form, but that's a super simple example, obviously far away from a neural network and yada, yada, yada. But I do want to say that the perturbation thing was important because it may be the case that the mutual information is too large. So M of X is very correlated with X because of the particular function M. So what happens here? Well, I'm not going to allow you to expose M of X. I'm going to perturb M of X, the multidimensional M of X, with this B noise vector and expose that, right? So now I'm thinking about the mutual information as being X connected to M of X plus B, which is different from M of X. And the more noise I add, the lower I can drive this mutual information. And in order to get this right mathematically, we're going to add continuous noise. And even if M of X were discrete, we're going to essentially output a continuous variable. Of course, the adversary could take M of X and truncate it down if they wanted to use M of X. But what we expose is going to be in the continuous domain for the D outputs of M of X, right? So we're going to do this perturbation so we can control the mutual information. How do we do that? Well, I have to get to that. What we want is to not have to do complicated analysis. So in differential privacy, people write papers for a particular M. So if M were an algorithm like k-means clustering, you would compute the global sensitivity for k-means clustering, and you'd carefully then analyze the epsilon and so on and so forth when you jiggle the output or jiggle the input, and you could do that in differential privacy. We want to think about M as being a black box, but we're going to be allowed access as an analyzer. We want to be allowed access to M, so we can run M on fake data that comes from the same distribution. And you'll get more about that in a minute. But think of M as being a black box. I can't really see inside of it, and that should be okay. If you can see inside of it, that's fine. And in some cases, you can do better. And I'll say more about that too. So if the mutual information that we can hopefully automatically compute using M as a black box is not sufficiently small, then we want to create a scheme to perturb M of X such that it produces a satisfied bound on mutual information that corresponds to the security parameters. And that mutual information bound is going to control the posterior advantage, and that might be actually the security parameter, that you don't want to have more than a 1% improvement in the failure rate, increase in the success rate, and so that's how you figure out what the noise is. And if you're only focused on the posterior advantage, then the data distribution and generation can also be black box. So you just say, I don't know the distribution, I can't give you a closed form for it, but I can continually sample from it because I have a program that allows me to sample from the universe and get an X sample from the universe. Right? So, okay, great. And so one more equation here, and it's the last one, I promise. What do we have here? So this is the basis of automatic analysis, and there's a bunch of things to parse here. On the left-hand side, we have the mutual information between M of X plus B now and X, right? On the right-hand side, we have a bound on this mutual information, and you have a determinant of a matrix. That's what DET stands for, and you see the covariance. So first, let's think about sigma M of X as being the variance of a single dimensional variable, and sigma B as being the noise, and you have a single variable in the noise. So what are we saying here? We're saying, look, if I'm sampling from the distribution and I'm exposing M of X, and I'm doing many trials here, I'm going to look at the variation in M of X. So I'm taking 5 out of 10. I have a universe of 10 numbers. I'm sampling 5 of these numbers, and I'm publishing the average. I run this experiment over and over and over. And I look at the variance in the exposure. So I'm going to see things that are close to, let's say, 5 if the numbers are between 0 and 9, roughly speaking. I mean, maybe 4.5 or what have you. But it's going to be what is the variation there, right? Obviously, as the number of trials increase, the variation changes. But let's say I run enough trials. So if there's significant variation, that means my sigma M of X is large, and I'm going to have to need my sigma B to be large as well, right? But if I'm getting exactly the same thing over and over for the M of X, well, basically I already have Shannon perfect secrecy, and I don't have to add any noise because I got essentially 0 for a sigma M of X, right? So there's an inverse relationship, and this is the intuition. There's an inverse relationship between the variance of M of X and the noise that I need to add. So the greater the variance, there's a proportional relationship between the variance of M of X and the noise that I need to add. because I want this quantity sigma m of x divided by sigma b to be small. So as sigma m of x increases, sigma b needs to increase as well. Right? So I'm going to have to add noise with larger variance, which means that any given noise that I add, obviously noise is also going to be sampled from this distribution, but I'm specifying the variance for it. That's going to get larger for a particular trial. Right? So in general, we're going to end up having covariance matrices corresponding to d by d covariance matrices, and I'm not going to get into that, but hopefully you got the intuition for a single variable output for m of x. Right? So if you had something that you were producing the max and you were sampling from a distribution, we are publishing the max. It's entirely possible that the variation in the max would be much larger than the variation of the mean. In fact, that's going to be the case for most distributions. In this case, now you have to perturb the max because you are going to have more variance, and you're going to have to perturb it much more than you would perturb the mean for m of x. And so then you end up with a little bit more with respect to exactly how you control it. So there's two things here. You got the equation corresponding to the bound on m of I, and then we're basically saying, you know what, we can discover the covariance of the covariance matrix of the noise, and we can control this m of I x and m of x plus b to be less than whatever quantity we want. We ended up picking 1/2 in this example here, right? And this covariance matrix is going to be related in the multidimensional case to the eigenvalues of the covariance matrix of m of x, right? So again, intuition is in the multidimensional case, you're going to have a geometry corresponding to the distribution of m of x, and this noise is going to have to fit the geometry. Where you have large eigenvalues, you're going to add noise with more variance. Where you have small eigenvalues, you're going to add noise with smaller variance. And if the eigenvalues are 0, then you're going to add, you don't have to add any noise. Right? So that's what you want to take away. It's the noise that you add is anisotropic. It's not the same noise in each dimension. Okay. So this is important because it may be the case that you have low rank spaces. You may have a d-dimensional output, and a lot of the outputs could be stable, and only a few of the outputs might change. And only for the outputs that are unstable or that the output change, you have to jiggle those outputs to make sure that the adversary gets a posterior advantage is bounded because you bounded the mutual information. Right? So it may be the case you have D, which is growing, which is large, but the amount of noise that you add could be order 1, as that last line of the slide says, because that's related to the eigenvalues, the non-zero eigenvalues. Right? So it may only add constant noise. All right. So we're going to look at the algorithm, which is a Monte Carlo simulation, and then we're going to spend the rest of the time in examples, hopefully putting all of these things together. Right? So the way this analysis is going to work, as I said, is going to be automatic. We have our distribution. It's a black box distribution. I can constantly sample from it. I'm going to run n trials. Right? I'm going to sample x1 through xn. For each of these trials, I'm going to compute m of xi. And I'm going to get m of xi for each of these things. I'm going to determine the empirical covariance. And this is an estimate. That's why it says sigma to the m of x for m of xi. Right? So all of this can be done using MATLAB, for example, using a few lines of code. We can now do the eigenvalue decomposition of this covariance matrix, and we find the eigenvalues and the eigenvectors. All right. So this is linear algebra. So basically, what you want to think about, the way you want to think about this is, we haven't done any exposure yet. We're doing analysis. x1 through xm are fake data. The eigenvalues and the eigenvectors, as I said before, but I'll repeat, are the power of the output distribution along each direction. You have greater power when you have larger eigenvalues. Right? So all of this is just analysis, but it's done automatically. Now you get ready, you want to release something. At this point, you're going to sample x from D again, and you're going to generate, using that theorem I just showed you, generate noise that fits the geometry of the m of x distribution. It's going to be anisotropic noise, B, where the variance of B along a particular direction a particular eigenvector, is going to be proportional to this eigenvalue. And then you're going to release m of x plus b. So you're going to perturb each of the outputs of m of x by sampling from this anisotropic Gaussian noise, which is the way I described to you. So you're going to possibly add, for the unstable outputs, you're going to sample from a larger noise variance for that, and you may be adding 50 to that. And for a very stable output, you might say, well, I can just expose this output corresponding to m of x. Okay, so that's it. That's essentially packet privacy, operationally speaking. It's based on these two theorems, and essentially what this says is you controlled the mutual information m of x plus b by essentially choosing b appropriately. That bounded the posterior advantage, and depending on what you want for the posterior success rate, or maybe you're just focused on the posterior advantage, you can say that the adversary failure rate only improved by 0.01 because you added this much noise, or it improved by 0.1 because you added less noise. Okay, so the last thing I want to do is go through a few examples, trying to put this all together, and then I'll close with a whole bunch of questions, and there's some limitations. Oh, I should say that so far so good. Things are automatic, etc. But as you can see, there's some computational costs associated with packet privacy, but I'll get to that at the end there. So let's do some simple examples, and I also want to specify everything here. The data generation, M, and all of that. So one way that you can get a distribution very easily that's characterized, like I said before, what does it mean to say that I have CFAR10, which is a collection of images of animals? What does it mean to say that I have cat images? What is the distribution corresponding to cat images or people images? So the way you want to think about this is, let's subsample. Okay, let's say you have some sensitive data. It corresponds to CFAR10 or MNIST, right? It's sensitive data in the sense that the adversary hasn't seen the data, but the adversary has context, knows that there are numbers associated with this and they're handwritten images or what have you. So how do you characterize the prior knowledge of the adversary mathematically in this case? Difficult. So what we do is we go conservative. We essentially say, let's pretend that MNIST, which is the sensitive data, is completely public, right? But my distribution is subsampling. When I expose m of x, the universe U is all of MNIST, which I'm going to publicize, but x is going to be 50% of MNIST, randomly sampled, or 30% of MNIST, or 90% of MNIST. Okay, so there's entropy that's created because of subsampling, and now I've specified the distribution very simply because it's essentially something that says I randomly selected IID 35,000 or 70,000 MNIST samples, or I selected 30,000, right? So super simple. You have a strong interpretation here, and this is a little bit similar to differential privacy, where you're assuming a strong adversary. You're saying that adversary knows the universe. It actually may be the case that these lung scan images that came out of hospitals are never exposed to the adversary. But you're going to pretend that all of these lung scan images came, but are exposed to the adversary. I'm going to subsample from them, 90% of them, and I'm going to create a neural network training model corresponding to these subsamples. And I get entropy this way, even though the adversary knows the universe. In reality, the adversary is going to have a harder job than what packet privacy is going to tell you with respect to its failure rate, because the adversary doesn't know the universe. But we have to get our distribution somehow, and the easiest way is to use subsampling. So yeah, so you can always use subsampling. Obviously, there's a little cost associated with it. We'll get to that in a second, because you're not necessarily using the entire universe to do your training or what have you. But most of the time, people use subsampling for robustness, for stability. So there's a lot of good reasons to use subsampling. All right. So now let me tell you a little bit more about this example. Right. So what we're going to do is do a toy machine learning example, and then I have a little more complicated one. We're going to train a 3-layer fully connected neural network. So it is a toy example on the MNIST data set, right? We are not going to use the entire MNIST data set. We're going to use half the data set. We could have used 80%. It's just an arbitrary choice. We're going to do the subsampling, and we're going to expose M of X. Okay. So what would we do now? To analyze this, we would go to this algorithm that we described, where we're going to generate fake data X of I, and we're going to generate 35,000 samples randomly selected. We're going to run this neural network training a number of times and get many different neural networks. None of these are exposed, and look at the stability of the neural networks across the parameter space. So let's say that we had hundreds of parameters, because D is now in the hundreds. We look at the vector of parameters, and we're going to generate, a whole bunch of these trials. It turns out you need, tens of trials, and we look at the eigenvalues and the eigenvectors corresponding to the M of X space, and we figure out that some of these parameters are very stable, and some of them vary a bunch. And these parameters that vary a bunch, we have to jiggle. We have to find the noise matrix corresponding to the particular dimension of the neural networks, the particular space of the neural network parameters, and we have to add a noise to that, right? So if you do all of that and go through this, and you say that I want to fix the mutual information of X and M of X plus B to be less than or equal to 1, you have to add a little bit of noise, because you get fairly stable things in the STOA example, and the overall magnitude of the noise measured as the norm here is 3.7, right? So that number is important. If you did this without adding noise, non-privately, but you did the subsampling, you end up getting, let's say, 95% accuracy. It's 94.8 in this case, but obviously that changes depending on how much you run, how many times you run, and whether you ran for more iterations, etc. The amount of noise you need to add in order to get this mutual information bound of 1 is some quantity 3.7. And when you add that noise and jiggle these neural network parameters, the neural network is not as efficacious as it was before, but the accuracy drops by about 1%, right? So this really puts a whole bunch of things together. It also tells you that there's a privacy utility trade-off corresponding to if you want more privacy, you want the mutual information to be smaller, your noise is going to be larger, and your accuracy can potentially drop because you added larger noise, right? But this is just one example, and you could obviously run this for different parameters many times, right? And you get different numbers. So there's one last thing that I want to say, which is when I said non-privately here, corresponding to the trained.neural network, this was many runs without adding noise, but with 50% subsampling on MNIST. If you use the entire MNIST, you could probably get better than 95%, but I didn't bother with those numbers because 50% was subsampling was just an arbitrary number. You can do this experiment with 90% subsampling. You can't do it with 100% because then you have no entropy. There's no distribution here, and the adversary knows the universe. But even if you did high rate subsampling, and it was in the 90s, you would get some entropy and you could get security proof. Right? So one more example, which is a lot more interesting and has a few more interesting aspects to it, which is k-means clustering. So what are we doing here? We're saying that M is a fairly complicated algorithm that does non-convex optimization, takes a data set corresponding to unlabeled data and clusters it into k clusters, as you can see here, right? So that's our k-means clustering, right? And the algorithm is black box. It could be thousands of lines of code, right? We want to now analyze the pack privacy of k-means clustering, and what we're really saying is if we expose these k centroids, right? So what does it mean to expose the clustering? Well, basically, it's equivalent to saying that I'm exposing the k centroids, okay? Because once you have the centroids, you pick, you create the clusters by choosing the centroid closest to any given point. So you run through all the points, and if the green points are closest to the leftmost centroid, the blue points are closest to the rightmost, and the red ones to the bottom one. Right? So the k centroids are the exposure. So M of X is producing the k centroids in a k-means clustering algorithm. Right? So again, setup is maybe we have sensitive data that's unlabeled. I'm going to pretend that all of this data is known to the adversary. And then I'm going to run the k-means algorithm on subsample data, whatever algorithm that I was given. And that k-means algorithm is going to produce a bunch of centroids, k-centroids. Now, with those k-centroids, I can do the clustering, and obviously it's equivalent, hopefully. You realize that the k-centroids define the clusters. So I want to now, if I want privacy, I might have to jiggle these centroids, which obviously jiggles the clusters, and my pack privacy analysis is going to tell me how much I'm going to jiggle the centroids. Okay, and if I jiggle the centroids a lot, then my clusters aren't going to be optimal. Let's say that the non-privately, I can get, even for this non-convex optimization problem, I get lucky and I get the optimal centroids. And the cost function here is this argument cost function that I won't bore you with, but it's basically, you know, the sum of squared distances, right? You can define the optimality of k-means clustering in many different ways, but a classic way is to essentially say, I'm going to define a loss function or a distance function, and this cluster is better than the other cluster because I, you know, appropriately to minimize the square of the distances. And so now you say, well, if I created an optimal clustering, and but for privacy, I had to jiggle the centroids and then create a suboptimal clustering, then whoa, you know, I end up getting a greater distance, and therefore I got some problems. So there is going to be a privacy utility trade-off, right? But the outputs are the k-centroids, the mu i's, and my goal is now to minimally add noise, right? And pack privacy will allow me to do that, right? So the setup would be that I don't use the entirety of the labeled data set. I choose some sampling of the data. I generate the k-centroids. I run this over and over. I compute the covariance. I figure out how stable this k-means algorithm is, and I figure out how much noise to add, right? So if you go do that whole process, you can basically do a pack analysis, right? So we did that, and essentially we ran a black box k-means algorithm on a n subsample subset of the entire MNIST data set. We did this analysis on using the k-centroids to determine the clustering, and basically the results look really bad in terms of stability. So then we started looking at it more carefully, and we said, okay, why is the case that we're getting very unstable, even though we did 90% subsampling, we're getting very unstable centroids and with a lot of variance. Well, it turns out that non-convex optimization has random initialization. So we're using MATLAB to run this, and when we ran this over and over, we ended up with non-convex optimization creating problems for us, in the sense that even if the data set were exactly the same, because of the random seed and initialization, we got different centroids for the same data set. So forget it if you change the data. You obviously would get different centroids for two reasons: because the data is different, and because the random seed and the initialization gave you a different local minimum. But it turns out that MATLAB has a feature, and most k-means algorithms obtain stability by repeatedly running different random initializations and averaging the result of the k-centroids. So you get k-centroids with random initialization 1, a different k-centroids with initialization 2, etc. And then you do the averaging of the centroids, you know, with some sorted order, let's say left to right or what have you, and that's the output that you produce. And this gives you better results. It also gives you more stable results. And so we used that algorithm, which had this internal loop corresponding to averaging over many local minima. And that algorithm is much more stable, not just for the same input, but also for different subsample inputs, especially if they're close to each other. So, so in this case, the robustness of the algorithm that improved the efficacy of the algorithm essentially produced an algorithm that was better for pack private analysis. And we're seeing a lot of this as we explore, but this is a good example, and I'm not going to go too deep into other examples. So when we did all of this, we realized that the averaging reduces variance, so that was nice for us, even across the different subsamplings. And I'll just leave you with giving you some sense of what the numbers look like if you actually run this on MNIST, right? So again, we fixed the mutual information to be 1, and we looked at k equals 2 to k equals 10, and we're subsampling 1,000 samples out of 70,000, right? So if you keep doing this, you get very different samples that correspond to the 1,000 if you're randomly sampling from 70,000. But the actual centroids, the pair of centroids that you get for the 1,000 samples versus a different 1,000 samples are quite close to each other because you end up the 1,000 samples are quite reflective of the entire data set. So people do subsampling for efficiency, and if the subsamples reflect the data set, you get essentially the same results as running the entire data set. And that's basically what these results tell you. If you choose subsamples of 1,000 to 10,000, if you go down the first column here, you can see that you're basically getting the same centroids. So because of that stability, the amount of noise that you need to add is going to be a function of the 3% or the 1% that you see here. And I'm not going to tell you, what the exact noise vector is and so on and so forth. This was really giving you the highlight on how subsampling in certain cases can give you stable outputs, and the k-means algorithm is one such where you can get that if you do this averaging thing. Now, if you have larger k, it makes sense that there's more radiation and that there's more instability because k equals 10 has 5 times the outputs as k equals 2. And here you might have to do more subsampling, not just 10,000 or 70,000, but if you wanted to get the stability to be less than 25%, 5% or what have you, you'd have to go to maybe 1/2 of MNIST being subsampled and so on and so forth. So the overall flow here for privatization would be that we would do the subsampling and we would find the privacy utility trade-off. I haven't given you the explicit trade-off, but you do get some sense of it from this example, which says as the numbers, 56% over on the top right shrinks to 25%. That is essentially something that tells you that the utility is being affected, but you can improve the utility by doing larger subsamples. And if you had a more stable algorithm, it would be more easily privatized. All right. So let me close. So what I've described to you, hopefully you get some, you have some sense of what packet privacy is from this presentation. But it's basically an automatic analysis strategy, and the way we make it automatic is by doing Monte Carlo simulations. We do need to assume, unlike previous approaches, that the private data is from some distribution. If you had some distribution of, let's say, salary data or other attributes, you could certainly use that distribution. But most of the time, you don't have distribution for your data sets like CFAR10 or MNIST. So the way you generate a distribution is through subsampling. It's this conservative strategy. If your distribution is a subsampling distribution, it may be the case that you can definitely do automatic privacy analysis, but in many cases you can have order 1 noise if you have essentially a low rank space, right? And we're finding that in many examples, including machine learning, we don't have to add noise that grows with the dimension as you would with differential privacy, but because these large spaces are quite sparse in terms of their non-zero eigenvalues, right? But I want to leave you with this, I think, bigger idea, which is this connection between algorithm stability and privacy. And privacy can be measured and packed using small mutual information. And then the connection to stability and generalization error is separate from security, but there's that connection as well, right? So what I want to leave you with is this thought. Suppose I have a giant data set. I kind of have to subsample from it because I can't handle the entire data set. But I want to learn from this data set. I want to create a model that learns from it and give it to people so they can use it, in ChatGPT or use it to determine if people have cancer or not, and yada, yada, yada. So if I'm getting the same neural network with different subsamplings of this data set, That basically is a model that is generalizable. Basically, what generalizability says, what low generalization error says, is that you're getting the same model regardless of the input data. There's stability associated with, you change the input data a little bit, it doesn't matter, you get the same result. That result is generalizable in the machine learning space. The beauty of this, and this is the final thing I want to say, is that this stability and low generalization error is easy to privatize because it kind of has small mutual information, numerically speaking. And therefore, the noise that you need to add to this output to get privacy viewed in terms of fact is going to be much smaller. In fact, if you had perfect stability, you wouldn't have to add any noise, but you would have perfect generalizability. Okay? So I'll leave you with that. I'm happy to answer questions. I have no idea how I did in terms of time, but I'm happy to stick around and answer a bunch of questions. And so let me close out here so I can look at people. Yeah. Hi.